Good day, ladies and gentlemen. This is the 7th lecture in the second series of lectures related to the implementation of the RM software for filter design. In this lecture, we will represent the synthesis of amplitude-corrected selective monotonic filters. That means that the existing polynomial monotonic filters will be upgraded or extended with transmission zeros in order to improve the selectivity and the passband performance. Since the same method was used for non-monotonic filters, where Chebyshev filters were used as a representative, here and the zeros were distinct. Here, to make the story shorter, among the two possibilities, distinct or multiple transmission zeros, we will use the second one, and we will show how a critical monotonic polynomial filter may be upgraded into a selective, again monotonic, rational filter with multiple transmission zeros. Here is the content: naming the project, introducing the design requirements, synthesizing the transfer function, analysis of the solution and system realization, passive LC, active RC and SC, and digital infinite impulse response realization. We start by activating the main program, RM1, allow blocked content, and look to the recommended design sequence to make our plan. First, we will enter the project name, then the design requirements. Then we will produce a CMAC filter. In this case, it will be not the LSM, it will be, for example, the Halpern filter. And then we will go to the amplitude correction, and we will go with Chang MZ, which is different to the one which was used for the Chebyshev filters as an alternative, and we will get multiple zeros. So one should have in mind that it's a unique property or capability of the RM software to have multiple zeros. And finally, we will proceed with the system synthesis. So the name will be corrected Halpern. The filter is low pass, and here we will enter the design requirements. This means 100 kilohertz will be the cutoff frequency. We are speaking about selective filters now. We will use, for example, 130 to be the upper frequency of the transition band. The maximum passband attenuation here is usually 3 dB, since it is monotonic. Minimum stop band attenuation will be again 40 decibels. A minimum asymptotic slope. Here we will leave the opportunity to have maximum number of transmission zeros, so it will be 6 decibel per octave as a minimum asymptotic slope. The value of the group delay error doesn't make sense, but it is compulsory, and the normalization resistance is 1 kilo. Now we will proceed to the transfer function synthesis. It will be critical monotone, CMAC, and we will use Halpert number 3. And now the program is offering that the filter should be of the order 12. Since, however, we will introduce transmission zeros, we will reduce the order of the filter according to the number of introduced zeros. We will use here, for example, 9. And that is all. Now we can run the synthesis of the polynomial filter done. We go now to the amplitude or phase correction, and we will introduce multiple transmission zeros. The program is Chang MZ, and it will ask for the number of transmission zeros or the order of the nominator. It was 9. We will, the order of the filter is 9. We will put 6, which is a freedom which is also unique to the RM software. So we can put any even number lower than the order of the filter. And now we will synthesize we will introduce the transmission zeros, already done. And now we will proceed with the analysis of the properties. Analysis of the properties. It is a low pass function, low pass. Done. Now we will look for the output files, and the CSV file is of main interest. Here is the time domain response. This is the time domain response. As you can see, it needs time to settle, which is a property of this kind of filter of Halpern. Now we will go for the frequency domain characteristic. And here is the solution. We will make copies. Now, the first thing of interest is the attenuation. And we will enlarge here to see only the attenuation. Here it will be only 50 decibels. And we will go to 150 kilohertz only. And what we can see here is a wide range. So we will put a little bit more freedom here to see 250. We can see here a wide interval in the stop band in which the attenuation is extremely high. So if you have some disturbance here in this region as an intermodulation result, something which must be suppressed before entering the transmission channel, then this kind of filter will be perfect for the application. It will suppress it even though it has some instability, some kind of changing in time. Now we will look to the passband. And as you can see, the amplitude characteristic of the, or attenuation characteristic of the Halpern filter is dramatically improved, since the attenuation here is 100 dB. The attenuation is much smoother and much smaller in the passband than the original, which has a stairway shape of amplitude characteristic like this. So now we will go for the phase characteristic. Here it is. Highly distorted at the end, which will be best seen at when we look for the group delay. Here is the amplitude, and here is the group delay, which is really sharp at the end, which is property of all selective filters. So analysis done. We will go now to the report textual to see how the main requirement about selectivity is fulfilled. And it says that the transition region is only 13% of the passband, while we were asking for 30%. So that means that we may go with a lower number of transmission zeros, or with a lower order of the filter, for example, 8th order of the filter. Now we will proceed with the synthesis. This is the passive LC for low pass filters. Done. And now we will look for the spice. Here it is. Now I will here reduce the so that is the halter filter with triple transmission zero group delay. As you can see, there is a sharp rise of the group delay at the end of the passband. Okay, now we will look to the schematic. So a capacitor in the parallel branch, inductor in the series branch, and then 3 cells generating the transmission zeros and the capacitor at the very end. This concludes the description of the schematic. Now we will go for the cascade RC realization. Done. And here is the spice file. Of course, it's the same. The schematic. It is 3 second-order cells representing the transmission zeros, 1 second-order cell with a zero at infinity, and 1 first-order cell with 0 at infinity. Then we will proceed with parallel RC realization. Here is the spice file. Of course, all the same. And here is the physical realization. Four second-order cells, 1 first-order cells, all connected in parallel. This is the summing and the details of the summation. And now we will proceed with the SC. The sampling frequency will be set to 10 megahertz and the normalization capacitance to 10 picofarads. And we will run the program. Now we will look to the spice. And again, the simulation is performed at the middle of the passband, 0.5. This is the output of the second anti-aliasing stage. And it will take time, we will not wait for it. And finally, Now let's look to the schematic. So 1, 2, 3, 4 second-order cells connected in parallel, 1 first-order cell connected in parallel, the summing and the details of summing, including sample and hold and the structure of the overall system. And now finally we will go with the infinite impulse response. 10,000 kilohertz is the sampling frequency, and the synthesis is done here. We will look to the CSV file to see the resulting response in the frequency domain. And of course, everything is the same. Now, this concludes our design process. We have everything we need, the schematic, the poles, zeros, and so on and so on, for every kind of realization. The properties documentation, as you can see, there is a so large number of documentation. One is recommended to copy the whole directory at this stage to have complete information for the design process. And now one may proceed with start design, since it comes that a simpler solution may be developed to save the number of components during realization. So that will be all. Thank you very much for your attention.